Recall that independence is at its heart a rule of products. As we had already seen in Tableau 9, Part 1, in the case of a composite experiment in the discrete setting, a product space was engendered with a product measure obtained by multiplying individual mass functions. This intuition carries over seamlessly into the continuum, with the proviso, of course, that the mass functions in the discrete domain are replaced by mass densities in the continuous domain. As George Polya suggests, it is always wise to begin with the simplest non-trivial version of the problem, and in this case, the simplest non-trivial version involves two independent trials. Accordingly, consider two trials leading to continuous chance variables, random variables, say x and y. X is governed by a density function, say p sub 1. Y is governed by a density function, say p sub 2. The trials are said to be independent if together they engender a composite experiment where the sample space is described by a pair of real numbers. In other words, the sample space is the Euclidean plane. And the pair of real numbers forming the composite outcome of this experiment are governed by a mass density in two dimensions, which is separable into a product of two one-dimensional mass densities. This is very much what we saw in the discrete domain. Now, why does this imply independence in the sense of multiplication rules for events? Well, the argument goes in exactly the same fashion, sums segueing into integrals. So, to verify independence, suppose A is a subset of real numbers, B is another subset of real numbers, and we want to know the probability of the joint occurrence of the events that the first outcome x is in A and the second experiment's outcome is in B. So now we have a composite experiment with two individual experiments composing it. What does this look like? Well, naturally, we are thinking of events as sets. A is a subset of the real line, in this case I've shown you an interval. B is another subset of the real line, another interval in this particular example. And we're interested in that set in the plane for which the first coordinate variable lies in A and the second coordinate variable lies in B. Of course, you recall that we call this the Cartesian product of A with B. And so the event at hand is the set of all pairs x, y, for which x lies in A and y lies in B. In other words, the Cartesian product of A with B. If A and B are intervals, then the Cartesian product is a rectangle, as you say. How do you compute a probability? Simply accumulate the mass density over the region of interest. Or in other words, integrate out the mass density over this Cartesian product. Naturally, when faced with a two-dimensional integral, we simplify by writing it as an iterated integral. What is the region of interest? Well, x has to lie in the region A, and y has to lie in the region B. And so we have now an iterated integral. And we observe that the integrand, since it's separable into a function of x and a function of y, the integrand separates into two pieces, and therefore so do the integrals. And so we promptly write our integral down as a product of an integral over x with an integral over y. Now we stare at the expression on the right. The first integral is the integral of the density function of x over the region A. And of course, this stands for the probability that the first coordinate variable lies in A. Likewise, the second integral is the integral of the density function of the second coordinate variable over a region B. It stands for the probability that the second coordinate variable takes values in B. Take stock. The probability of the joint occurrence of the events that x lies in A and y lies in B is a product of the two probabilities that x is in A with the probability that y is in B. Or in words, events specified by x alone are independent of events specified by y alone. If we specify for the composite experiment in the product space a product measure which is inherited from a product of two mass densities, then this implies independence for all events specified by x with respect to events specified by y. Right. Now, once we understand this, we very quickly generalize to a general setting with, say, n trials. Imagine that we have n individual constituent independent trials resulting in continuous variables, and now we're going to need a more cumbersome notation. Right? We have now n variables to deal with. Naturally, we'll identify the trials by subscripts 1, 2, 3 up till n. Let x sub 1 be the first coordinate variable, x sub 2 the second variable, x sub n the last variable. Each of these experiments is governed by an underlying probability law. x1 has a mass density function p1, x2 has a density p2, xn has a density pn. By saying that the trials are independent, we mean that the composite experiment gives rise to a vector, an n-tuple of chance variables. The sample space here is implicitly n-dimensional Euclidean space. And the probability measure is inherited from a product measure where the joint density of these n variables is factored, is separable into a product of each of the n individual mass densities. Verifying independence follows the same pattern. Suppose A1 is a region on the real line, A2 is another region, AN is still another region. What are the chances that the first coordinate variable lies in A1, the second coordinate variable lies in A2, and so on, with the nth coordinate variable lying in AN? Naturally, we integrate out the joint density, the mass density, which now has units of probability mass per unit n-dimensional volume, integrated out over the region of interest, which is the Cartesian product of A1 with A2 and so on through AN. This n-dimensional integral simplifies again because the integrand has separated into a product of individual one-dimensional functions. And so this integral separates into a product of n one-dimensional integrals. Each of the integrals on the right represents a probability. And so we find that the right-hand side devolves into a product of n individual probabilities. And again, we verified a rule of products. The probability of x1 taking value A in a region A1, x2 in a region A2, and so on, xn in a region AN, is a product of the individual probabilities. We verified again that events specified individually by x1, x2 through xn are independent. But if the student looks back at the argument, she will realize that essentially the same argument carries through for events specified by disjoint groups of these x's. All that happens is that the integrals will now separate into one group here, one group here, one group here, and again you have a rule of products. Again, independence is manifested in a product space when we have a product measure.